If your DGCA exam is within the next 2 weeks, you need high-density, high-retention data. We are stripping away the fluff for a data-dense synthesis of the 5 primary navigation aids. Every aviation nav aid is defined by 3 intersecting data points: its frequency band, its emission code, and its primary systemic error. This chart shows the master quick reference table we will build today. We divide the 5 systems, VOR, NDB, ILS, DME, and GPS, into 4 operational quadrants. Each quadrant breaks down the underlying physics of the system, followed immediately by a rapid recall drill. You will get the exact exam question, a strict 2-second pause, and then the answer. Spatial mapping, connecting frequencies to their physical limits, is the only reliable way to manage this high volume of regulatory data. Quadrant 1 covers non-precision bearing systems, starting with VOR and NDB. VOR operates in the very high frequency, or VHF band, from 108 to 117.95 MHz. Its emission code is A9W, telephony combined with frequency or phase modulation on the main carrier. This animation illustrates the primary sight error for VOR, scalloping. VHF uses line-of-sight propagation, so signals physically bounce off surrounding terrain, distorting the path. VOR provides bearing only. QDM is the magnetic bearing to the station. QDR is the magnetic bearing from the station. The non-directional beacon, or NDB, operates at much lower frequencies in the LF and MF bands, between 190 and 1750 kHz. The beacon alone uses the NON emission code. With voice added, it becomes A2A. The DGCA frequently pairs these as NON A2A. These lower frequencies create specific vulnerabilities. At night, sky waves reflect off the ionosphere and interfere with ground waves, causing night effect. Low-angle signals also bend when crossing shorelines, creating coastal refraction. Quadrant 1 Rapid Recall. Pause the video if you need more than 2 seconds. Question 1. VOR frequency range. 108 to 117.95 MHz VHF. Question 2. VOR emission code. A9W. Question 3. NDB frequency range. 190 to 1750 kHz LF and MF. Question 4. NDB emission code. NON A2A. Question 5. QDM versus QDR. QDM is magnetic bearing to the station. QDR is from the station. Bearing accuracy is limited strictly by how an electromagnetic wave interacts with the physical Earth. This table now shows Quadrant 2, the instrument landing system. This requires multiple components to create a precision approach. This diagram shows the Localiser providing lateral guidance in the VHF band between 108.1 and 111.95 MHz on odd tenths. The beam is plus or minus 10.5 degrees from centerline. For vertical guidance, a UHF glide path between 329.15 and 335 MHz pairs automatically, establishing a 3-degree descent angle. Along this path sit 3 75 MHz marker beacons. The outer marker pulses 2 dashes per second with a blue light. The middle flashes alternating dot dash with an amber light. The inner sends 6 dots per second with a white light. Quadrant 2 Rapid Recall. Question 6. ILS Localiser frequency. 108.1 to 111.95 MHz VHF, odd tenths. Question 7. ILS Glidepath frequency. 329.15 to 335 MHz UHF. Question 8. ILS Glidepath angle, 3 degrees. Question 9. Outer marker audio and visual, 2 dashes per second, blue light. Question 10. Middle marker audio and visual, alternating dot dash amber light. Question 11. Inner marker audio and visual, 6 dots per second, white light. Establishing a strict 3D precision approach corridor requires mathematically pairing completely different frequency bands to prevent signal overlap. Quadrant 3 shifts from bearing and approach to active ranging. Distance measuring equipment operates in the UHF band between 962 and 1113 MHz. It relies on the P0N pulse emission to calculate timing delays. This diagram illustrates the critical geometric difference. DME measures the exact line of sight to the station, the hypotenuse, labeled here as slant range. It does not measure the horizontal base, or ground distance. Because of this geometry, slant range error reaches its maximum when the aircraft is directly overhead. You calculate this overhead reading by dividing their altitude in feet by 6,076 to get nautical miles. The ground station has a hard processing limit. Once 100 aircraft interrogate the station simultaneously, it reaches saturation and activates DME Hold. Quadrant 3, Rapid Recall. Question 12. DME frequency range? UHF 962 to 1213 MHz. Question 13. DME emission Hold? P0N. Question 14. DME overhead reading formula? Altitude in feet divided by 6,076. Question 15. DME saturation limit? 100 aircraft. Ranging accuracy is an applied trigonometry problem, dependent on altitude and slant distance geometry rather than signal strength alone. For Quadrant 4, we move into orbital space. The Global Positioning System broadcasts civil signals on the L1 frequency at precisely 1575.42 MHz. This animation shows why getting a 3D position fix requires intersecting data from 4 satellites. 3 provide the spatial coordinates, and the 4th is mathematically necessary to correct receiver clock error. Receiver Autonomous Integrity Monitoring, or RAIM, requires even more data to ensure safety. You need 5 satellites for fault detection and 6 satellites to actively exclude a bad signal. The largest inherent error in GPS is caused by ionospheric refraction as the signal travels through the atmosphere. The system also used to suffer from selective availability, intentional signal degradation by the U.S. Department of Defense, but this was permanently disabled in May 2000. Quadrant 4, Rapid Recall. Question 16. GPS satellites required for a 3D fix. 4 satellites. Question 17. GPS civil frequency. L1 at 1575.42 MHz. Question 18. RAIM satellite requirements. 5 for detection, 6 for exclusion. Question 19. Largest source of GPS error. Ionospheric error. Question 20. What was selective availability? US DoD intentional degradation, disabled May 2000. Space-based navigation trades terrestrial terrain interference for atmospheric refraction and precise clock timing vulnerabilities. This chart shows the fully mapped database of all 5 core navigation aids. You now have a structured mental database for the 20 most crucial exam variables. Every navigational limit we've mapped today, from scalloping to ionospheric refraction, is a direct physical consequence of the frequency and emission type in use. Screenshot the table. Drill the timings. Good luck on the exam.